So hi everyone, my name is Anna, I'm a fellow at ESA, and I'm spoiling. And today I wanted to talk about spectroscopic survey of the 300 parsec sample of cataclysmic variables, but as you have seen, I've been quite ambitious about the work I was able to do when I submitted my abstract. So today I will actually present some preliminary results about the 300 parsec sample. So we have already heard what cataclysmic variables are. So these are compact interacting binaries in which a white dwarf is accreting from a low mass star. And I just want to remind you why these binaries are important. So they are the best laboratory we have to test the models of binary evolution. And moreover, some of them have the potential to become at some point supernova type 1a progenitors. And for this reason, it's important that we try to address the issues that Diogo already summarized in his talk. So Diogo did already an amazing job summarizing CV evolution, which is driven by orbital angular momentum losses. So as the system evolves, it moves from shorter orbital periods, crossing the period gappas, the touch binary, and then getting to the period minimum and then bouncing back as the donor star become a brown dwarf and stop shrinking in response to the mass loss. So we know we need at least 3 mechanisms to reproduce the observational properties of cataclysmic variables. So we need magnetic tracking, which we heard about from Karim. We need gravitational wave radiation, and then we need consequential angular momentum loss, and particularly the prescription by Matthias, in which this consequential angular momentum loss this consequential angular momentum loss mechanism is more efficient the lower is the mass of the white dwarf, seems to work quite well, as Diogo has already shown. And indeed, we already also have some observational support for this kind of mechanism being present in CVs. So we measure the mass accretion rate for a sample of cataclysmic variables white dwarfs. And you can see that if we have a look at the mass accretion rate versus the mass, we find this anti-correlation. So we see that system hosting low mass white dwarf accretes at rates that are systematically higher than system hosting high mass white dwarf. And this is in contrast with the models in which the evolution of CVs is driven only by magnetic wind bracking and gravitational wave radiation. So this result is telling us that in the evolution of CVs, besides magnetic bracking and gravitational wave radiation, we need an additional mechanism of angular momentum loss, which takes into account the dependency on the mass. And we can see that this works well also for the effective temperature. So these big points are observation in comparison with evolutionary tracks and the models here. And these are effective temperature as a function of the orbital period. And again, the effective temperature is a proxy for the angular momentum loss rate in the system, because the effective temperature is set by the mass accretion rate onto the white dwarf. And you can see if you only have magnetic wind bracking and gravitational wave radiation, there is this major disagreement, and the situation improves once we include an additional source of angular momentum loss that is mass dependent. So these are some observational evidence for the need of this additional source of angular momentum loss. But this is not all, because thanks to the advent of Gaia, we also had the opportunity to build the first volume-limited sample of object. And once you have a volume-limited sample of object, you can better understand observational biases, and you can have a look at the properties of the population. So back in 2020, we used Gaia DR2 to pin down all CVs within 150 parsec. And we built this volume-limited sample of object, which is made up by 42 systems. And we could estimate that this sample is 77% complete, and this is where these CVs are located in the HR diagram. So we have volume-limited sample. We can have a look at the properties of the population. So we measure space density and had a look at the period distribution. So as you already heard, we found a space density of 4.8 system for cubic parsec. And we found that the majority of systems are located below the period gap and found a relatively small fraction of period bouncer CVs. And if you compare this with the prediction of the standard model, you can see that there are still this disagreement with the majority of the system being predicted to be below the period gap, much higher space density, and a much larger fraction of period bouncer CVs. Situation gets better when we include the additional source of angular momentum loss, mass dependence. And in this case, the fraction of system above and below the period gap is in better agreement with the observation. Space density gets also in a better agreement, but we still have the problem of the missing period bouncer. So this model still predicts 80% of CV should be period bouncer, but we have about 7 and 14%. So what's the issue here? Where are the missing period bouncers? So if we have a look at the effective temperature of period bouncer, they are located in this branch, and you can see that they are hotter, which means that they are accreting at a higher rate than predicted by the model. And if they are accreting at a higher rate, maybe they are evolving faster. So if they are evolving faster, they are staying around for a shorter amount of time, and that could explain why they are not so numerous as we believe. But what could be driving such faster evolution? Can it be magnetic wind bracking in brown dwarfs? I don't know. And also, if this is a possibility, what's the final fate for these binaries? What do they become? Do they become detached white dwarf, brown dwarf binaries? And we should find them more or less at this orbital period? I have no idea. So this is a possibility, but there is also an alternative. And the alternative is that the 150 parsec sample is possibly affected by small number statistic. So we had 42 CVs, but we had only 3 confirmed period bouncer in the sample and 3 candidates, so only 6 systems in here. So is small number statistic affecting our results on the fraction of period bouncer? That's a possibility, and as you can guess from the title of my presentation, if we want to solve this issue, we need to study larger sample and explore bigger volumes. So we should go larger and go to 300 parsec. You might think, okay, this is an easy task because Gaia DR3 was all about binaries. So Gaia published, the Gaia consortium published a catalog of variable stars. There is a catalog of CVs, so we can just use that. But I just want to have a big warning here. So this is the sample from our work in 2020. These are confirmed CVs. And these are the CVs from the Gaia consortium. So you can see that they recover some of the CVs within 150 parsec, but they actually recovered only 18 out of 42. So this is highly incomplete. And also they have this cloud of faint objects located here that they classify as CVs based on their variability. But if you have a look at their Gaia parameters, you find that these are basically blended sources in which the variability just comes from a nearby bright stars. And also there are objects with poor astrometry, so some are M dwarf that have been moved here just because they flare and they can resemble the variability of CVs. So yeah, if you want to use this catalog of CVs, just be careful because there are contaminants and it's not complete. Okay, so what we did instead is to use this catalog built by Elmay Britz over the years. She has been doing an amazing job keeping track of all CVs, CV candidates that are discovered by a transient survey and spectroscopic survey. And I think on average there are 4 new CVs that are discovered per week. And she has been keeping track of all these objects. So we cross-matched that with Gaia, selected everything within 300 parsec, and we are left with 339 between CV and CV candidates. And since there are candidates in this sample, we need to have a look at those and try to understand if they are genuine CVs or not. So to do that, we combined that with observation we have been obtaining in the last 2 years with X-Shooter and OSIRIS, GTC. So we have been obtaining spectroscopic observation of many CV and CV candidates, not only limited within 300 parsec. And so we combine this spectroscopic observation with the catalog from ELME and pin down 212 genuine CVs within 300 parsec. And this is the final sample, and we can also estimate that it's about 50% complete. Okay, so now we can again obtain space density from this sample. We find 5.6 10 to minus 6 system per cubic parsec. And you can see here in comparison with the 150 parsec sample results, they are in agreement within 2 sigma. And you can see that with Gaia, and thanks to this larger sample and more robust against small number statistic, we are also capable of reducing the error bars. And again, we can see that our space density agrees with the prediction by Diogo, but is smaller than the prediction from the models, including only magnetic bracking and gravitational wave radiation. Yeah, for the period distribution, we find slightly different numbers compared to the 150 parsec sample, but we only have at the moment 162 CVs with orbital periods, so we should get more orbital periods for the other CVs in order to confirm these fractions. And finally, the advantage of having this spectroscopic survey ongoing is that we can definitely exploit particular X-shooter, because with X-shooter we get the entire spectral energy distribution from the near ultraviolet down to the near infrared. And if we can observe in the near infrared, we are capable of putting constraints on the nature of the donor, and so we can identify system with brown dwarf companion and find period bouncers. And in particular, at the moment, we have 12 confirmed period bouncers within 300 parsec, and I'm reporting here a fraction of 6% as a lower limit, because, yeah, this is work in progress. We still need to analyze the entire sample. So to summarize, we can see that within the 300 parsec sample from these preliminary results, we don't find major surprise compared to what we got within 150 parsec. Models from Diogo are still in agreement with the observation, but the problem of period bouncer is still there. So we still don't find the system in the large numbers predicted by the model. And yeah, this is work in progress, so there is a lot to be done. So of course we need more orbital periods. We should take full advantage of the Gaia spectra to identify unknown CVs, so to discover a new system and improve our completeness. We can use also the spectra, archival ones, also to try to obtain parameters for this object that can also be useful to improve the theoretical modeling. And also we have maybe the possibility with this larger sample to also try to derive the scalar height of the population, which is also a clue about the evolutionary timescales of this population. Yeah, and that's it. Thank you so much.
Questions?
Hi, Tony Rodriguez from Caltech here. What are the false positives? And is it like the ones that you suspected were CV candidates but then turn out to not be? And second, in getting the period distribution, is there some subset for which it's harder to measure periods from either archives or any of these photometric surveys? Like, could there be some bias there?
Okay. So for the false positive, so there are objects that shows variability on similar timescales to CVs. So for example, if you have a flaring red dwarf, it can be flagged as CV candidate because of an outburst. And so it will just go in the catalog because someone said, okay, this is a potential CV candidate. So you want still to keep it because you can't afford to lose any objects. So you keep it, and then later on you have to verify. Other contaminants, also young stellar objects, some of them similar variability, detached binaries, so everything that has variability on these time scales. For the orbital periods, So the question is if there are biases in getting the orbital periods.
Yeah, like can you recover orbital periods for all CVs in the 300 parsec sample?
Well, I mean, that would be ideal. We haven't thought about that, but what I would like to do is like start a monitoring campaign to try to obtain orbital periods. But yeah, of course, the inclination could, system inclination could affect your success in finding a period. I guess also the mass accretion rate, maybe for the very high mass accretion rate system, could be complicated. So yeah, I don't expect major observational biases in the sense. I don't think this would play in such way to favor one population in particular compared to the other. But yeah, maybe someone else can comment more on that if they have any opinion on that.
Who has the question? Ken? And you?
So most of these are found via transient surveys because of accretion disk variability, right? Is it obvious that like 100% of CVs have accretion disk variability, or do you have some sense of how many, like could you miss some because the accretion disks are quiescent?
Yeah, absolutely. So we can miss definitely like nova likes if they don't go. So nova likes are accreting at a very high accretion rates and they have a stable hot disk. So if they don't go in low states, so when the accretion rates drops and then the system becomes fainter by 3 or 4 magnitude. So if this doesn't happen, then you will miss the nova-like. And I think Keith found a nova-like which was like within 200 parsec just last year and wasn't known before, but also the low mass accreting one. So if you period bouncer or in general system very close to the period minimum, they are accreting at very low states. So they have outburst recurrence time of decades, and then you don't find them. And within 150 parsec, we had an object that was discovered only in 2019 and was like a 80 parsec distance and was found only in 2019 because he underwent into outbursts for the first time. So these are the systems that we can miss, but the completeness I'm reporting here comes from Sloan. And Sloan is able to find the system because you identify them from the spectra, not from their variability. So I think this completeness will take into account for this kind of low accreting.
So the period bouncers, you'd still be safe even if they're not outbursting.
Sorry?
The period bouncers, you're not going to miss like many more of them just because they're not outbursting.
With Sloan, yeah.
With Sloan.
So I think this 50% completeness, take that into account. And the systems that are missing here are definitely period bouncers, nova likes, and polars. Also polars, if they don't go in, if they stay in high states, then you don't find them if there is no variability.
Okay.
If you go back to your Gaia HR diagram, I was curious what those luminous CVs around GF5 are.
These ones?
No, to the left and above.
These
Yeah,
ones?
that
Oh, these one are the
population.
nova likes,
Yeah.
the one at the critical.
Those are the nova likes.
Yes.
Okay.
More questions? Doesn't look like. I have a question for you, but we can talk later. Where do these early type NCVs come from if you destroy them in the envelope? But let's talk about this later. Okay. Next talk. Thanks, Anna.